Hagoromochaik, I'm so sorry. I didn't want to use you for something filthy like this, but you see, natural log of 2 is actually really small, small, S-M-O-L. Good morning, snackers. Welcome back to your weekly dose of math snacks, even though it's not weekly, it's something like bi-weekly or something. Never mind. I hope you are hungry. We are going to do something pretty spicy today. We are going to try to calculate I factorial. And not like a certain someone did it back then, just giving the definition of the gamma function in its integral form and then just saying, yeah, if you type it into Wolfram alpha, it spits something out. That's not the point in this whole thing right here, okay? We are going to try to give this thing a rough approximation, but at first I would like to consider the gamma function of a complex argument. We haven't talked about this before, okay? And with this tool we can actually derive the length of this complex vector right here, because if you plug in a complex number into the gamma function, we are going to assume for now that this is going to result in a complex number. Okay, and we are going to do some simple complex analysis right here. Let us go ahead and get started. At first I would like to take a look at just simply, oh yeah, and I factorial is nothing but gamma of 1 plus I, okay? Keep this in mind, that's why we are going to take a look at the gamma function of a complex argument. Okay, let us take a look at the gamma function of the complex conjugate of some complex number z right here, okay? We are going to assume that z is of the simple form a plus I times b, so a simple complex number in C1, okay? Meaning what is our complex conjugate right here, okay? We do some simple complex analysis. If you have this as being z right here, our complex number, then the complex conjugate is just a reflection of this thing on the x-axis. Meaning this thing right here is our complex conjugate z line, z hat, whatsoever. I would like to denote it also as being z star for reasons that will become apparent in a few minutes, because it's kind of messy to write a really long line above an expression that's just not something that looks absolutely nice, okay? So what can we say about this thing right here? Okay, if this right here is the reflection on the x-axis, then the z conjugate has the form a minus ib, because we are now in the negative I direction, you could say, okay? And if you multiply, this is important, z and z conjugate together, we are going to get, well, just a difference of 2 squares, okay? This is something you probably know by now. If you have watched this channel, then you should be knowledgeable about this right here, okay, knowledgeable. Difference of 2 squares tells us that it's nothing but a squared minus I squared times b squared. I squared is -1, meaning plus b squared. This, by Papa Pythagoras, if you construct yourself a right triangle into here, is nothing but the length of this vector in the complex plane squared, okay? That's an important definition, and since it's a length in the Euclidean plane, you could say, in the Euclidean geometry, we can equivalently rewrite this as r being nothing but the square root of a squared plus b squared. Okay, simple, really simple complex analysis right here. But this right here is pretty important, because if we can show that gamma of z conjugate is nothing but gamma of z, but the conjugate of this, we can actually multiply this thing together with gamma of z and get nothing but the length of gamma of z squared. Okay, this is a really important thing. Now, we are going to dive right in. Let us prove this little fact right here. Now, for this I would like to just consider one of the definitions, so you could make use of any old definition of the gamma function right here. I'm going to use the Euler form, for example, okay? Now, this is going to give us 1 over z conjugate. If you don't know about the Euler form, take a look into the description. There will be links to the corresponding videos. And then we are going to get our infinity-integral of 1 plus 1 over k to the z conjugate power, that's already quite weird in itself, over 1 plus z conjugate over k. And now we have to show a few facts, okay? Because what we want to basically do is we want to track all those conjugates to the top, you could say, to the outside, okay? Meaning we kind of have to show that our conjugate is being preserved under, okay, you would have addition right here, for example, you would have multiplication of many conjugate terms, and also you would have something conjugate power, okay? That's quite weird. We are going to talk about all of those cases now, okay? Those are going to be simple little proofs. At first, let us start with the conservation of conjugate, the preservation of conjugate under addition right here. If we consider this complex number, okay, this one is a plus ib, and this thing right here is nothing but c plus id, okay, taking the conjugate is going to give us a negative sign, so this is a minus, okay, giving us I times b plus c minus I times d. We can actually factor out the I on both parts, collect real and imaginary part, leaving us with a plus c plus, okay, we can also factor out the negative sign, so negative I c plus d. Meaning this thing right here is nothing but the complex conjugate, and that's why I said we're going to have huge lines right here of a plus c plus I c plus d. And this in itself, this under the conjugate sign, is nothing but the conjugate of c1 plus c2. Okay, we are having our complex conjugate being preserved under addition. So this is something that holds right here. That's a simple little proof. Now we are going to move on with the multiplication. Now for the multiplication it's going to be a bit messier. Both parts as the conjugate. We are going to get a minus ib times c minus id, leaving us with, okay, we are going to have ac. We are going to have those imaginary parts multiplied together. I times I is -1. Negative times negative is positive, so a negative sign right here. And then we are going to get b times d. This right here is our real part of the complex number. Now we can move on and actually collect our imaginary parts. So we are going to have negative I on all those terms. I hope you can see where this comes from. Then we are going to have a times d plus b times c. Now, this thing right here is actually nothing but the huge complex conjugate of a times c minus b times d plus I, a times d plus bc. Now what is this right here? If you go through the same process once again, so just plugging a positive sign in here, you could say, you are going to see that this thing under the conjugate sign is nothing but z1 times z2. Okay, so this is nothing but z1 times z2, but the conjugate of this thing. So just go through the whole process again, just with a positive sign right here. And you can see that this part is going to pop out eventually once again, because you are going to have plus times plus is positive and I times I is going to be negative. Et voila, works out really nicely. Now we have proven that we can preserve it under addition and multiplication. All that's really left is to do this right here. It's preserved under exponentiation, you could say, however you say it in this case. So let's take a look at n to the z conjugate power. Okay, meaning this thing right here is nothing but n to the a minus ib. Now, how can we move on? Well, I want you guys to consider something. If we have a to the b power, this thing right here is actually the same as e to the natural log of a to the b power, and then you can bring the b to the front using the natural log properties, and you are going to end up with this right here. Meaning, we are going to be left with e to the n, natural log of n, I'm terribly sorry, times this chunk, a minus ib, leaving us in this case with e to the natural log of n times a times, okay, if you have e to the a plus b, that's e to the a times e to the b. Okay, so we can break this up if we distribute natural log into everything. So times e to the negative I, and then we are going to have the natural log of n times b. I've made a proof on this thing right here. This is nothing but Euler's formula, okay? This is being preserved right here. So that's e to the natural log of n times a. And this thing right here is going to weigh a to the cosine of natural log of n times b, and then minus, because it's the negative branch right here, I times the sine of natural log of n times b. Now, how can we continue from this right here? Well, as you might notice, I'm now proving the property of exponentiation on complex numbers and the conjugate. This thing right here in itself is nothing but the complex conjugate, that's the complex number with real and imaginary part, of Euler's formula, just with a positive sign right here. Okay, so this thing in itself is just a complex conjugate. Then this term right here is going to be the complex conjugate of e to the I natural log of n times b, leaving us with e to the natural log of natural log of n times a times the complex conjugate, I'm terribly sorry, of e to the I natural log of n times b. E to the natural log of n times a, that's a mouthful to say. It's nothing but a real number, and the complex conjugate of a real number is just a real number in itself, because a real number doesn't have this part right here, so you can say that's I times 0, okay? A real number, and it doesn't matter if you have negative 0 or positive 0, that's the same. So this thing in itself is the same as the complex conjugate, and we have seen that the complex conjugate is being preserved under multiplication right here, meaning the multiplication of this thing of the conjugates is nothing but the conjugate of the multiplication. But the multiplication is nothing but this chunk right here, is nothing but this, is nothing but this, but with the complex conjugate dragged to the outside basically. Okay, this was already a lot of proving to do, but it went on quite easy, okay? It's not too hard to do. Now, how can we continue from this point? How does this help? Well, now, let us take a look at the denominator at first, okay? We have 1 plus some complex number conjugate right here, okay? Complex number over a real number is just another complex number. So you can interpret this thing right here as being, for example, some, let's say zk right here, okay? But the complex conjugate of this thing. The conjugate is being preserved under addition. That's a cool thing. This works out. We have proven this. Then up here, we are going to have just the complex conjugate of this thing. Now, we are going to drag this thing into here, meaning what we have overall is 1 over z complex conjugate. And what we have up here is, I'm going to write a few things out. 1 plus 1 over 1 to the z power complex conjugate, and so on, up until infinity. Okay, I'm going to write out a few terms. Down here, what we have is z conjugate 1, z conjugate 2, up until infinity. Now, complex conjugate is being preserved under multiplication. This thing down here is just a complex conjugate of all those parts together. Now we have a quotient right here, and a quotient is basically just the inverse operation to multiplication, meaning our complex conjugate is still being preserved under multiplication, okay? That's just the same scenario right here. Meaning overall, this down here is just the complex conjugate of all those parts. Now we can bring the complex conjugate to the outside. Meaning, if we write all of this stuff out, we can actually say that this whole stuff is nothing but the complex conjugate of this whole thing. Meaning, it's nothing but the complex conjugate of gamma of z. That's a lot of stuff you have to prove right here. You can make use of different forms, so there are even arguments for the integral representation. But yeah, this is basically it. Now we have shown that the gamma function of the complex conjugate is the complex conjugate of the gamma function of z. And with this, we can now work, because we can multiply our gamma of z together with the gamma of the complex conjugate of z, and then we can see what we get, okay? Now, our main goal is to basically get an expression for our I factorial. But like I said, we are going to take a little detour and take a look at the modulus of I factorial right here. I factorial is nothing but gamma of 1 plus I. We're going to write it out. Gamma of 1 plus I. Like I said before, I would like to multiply together gamma of 1 plus I with its complex conjugate. Gamma of 1 minus I. Here's what we have said before. If we assume that gamma of z is going to spit out a complex number, okay, and we multiply it together with the complex conjugate, this is going to result in gamma of z times the complex conjugate of gamma of z. But we have seen before that this is going to result in a modulus of gamma of z, so the length of this complex vector, but squared. Now we can take the square root on both sides. It has to be positive because the modulus is defined positive, meaning overall that the modulus of our gamma of a complex argument is nothing but the square root of gamma of z times gamma of z conjugate. Okay, so this in itself is quite easy. We are doing the exact same thing here. So let's put a square root around this thing right here. And this is going to be the modulus of gamma of 1 plus I, meaning the length of I factorial right here. Now, we can make use of a nice definition of our gamma function right here, because gamma function of z plus 1 is nothing but z times the gamma function of z. Okay, this is something that holds for the gamma function. It's defined recursively, meaning this in itself is nothing but I, so reducing this argument by 1, times the gamma function of I. Now, this is absolutely beautiful right here. This expression right here is so Gucci, and when I first did this, I couldn't believe my eyes that it is going to weigh to a nice closed form. Okay, so this in itself is really ridiculous. I want you guys to remember Euler's reflection formula. If we have gamma of z multiplied with gamma of 1 minus z, okay, this is this here multiplied together. Okay, bear with me. It's going to weigh 2 pi over the sine of pi times z. Oh, my boys, it's so nice. Meaning, this thing right here is going to be modulus of I factorial is nothing but the square root of I times, and this multiplied with this together is nothing but pi. Okay, random pi popping up out of this. So amazing. Over sine of I times pi. How cool is that? And we can do even more simplifying. If we take a look at the sine as being nothing but its Euler definition. Okay, sine of z is going to be I to the I times z minus e to the negative I times z over 2 times I. If we now plug I times pi into here, okay, e to the e to the I times z is then going to be e to the I times I, so negative 1 times pi. So meaning overall sine of I times pi is going to be e to the negative pi, and then minus e to the negative I squared is going to be positive, and then pi, e to the pi over 2 times I. Now, this right here is quite a familiar thing, because if we now factor out a negative 1 right here, okay, this thing right here is the same as e to the pi minus e to the negative pi over 2 times I, just with a negative sign in front, and then we multiply both sides by I. We are going to get that this expression right here, I'm going to put it here, is nothing but, we have I times pi right here, over this thing right here is going to evaluate to, how should I put it? I am thinking about introducing the hyperbolic sign right here. This in itself is kind of the hyperbolic sign already. Okay, we are just going to put this in here. Okay, this is going to give us negative e to the pi, negative e to the negative pi over 2 times I. Now you see, if we take the reciprocal of this thing, I times I is going to be -1. -1 times -1 is positive, so this, that, and that is going to cancel out. And what we have down here, e to the pi minus e to the negative pi over 2, is going to be the hyperbolic sine of pi. Okay, so there's nothing but the square root of pi over the hyperbolic sine of pi. And we can make this look even more cool, okay, or you can take the reciprocal and then you have 2 times pi over e to the pi minus e to the negative pi, okay, this in itself is pretty quite cool, e to the pi and e to the negative pi, that's pretty dope. This is nothing but the square root of pi times the hyperbolic cosecant of pi, okay, this is just a different form, so 1 over the hyperbolic sine is nothing but the hyperbolic cosecant. Isn't that cool? This thing right here actually allows for a closed form of the modulus of this thing. And don't forget, the modulus of I factorial is the length of this vector. Okay, and if we square both sides, then this is nothing but the real part squared plus the imaginary part squared of I factorial. So basically what you can do is try to find the exact value of this thing right here. And then you can, for example, find out the real part through calculations, and then you can find out your b, the imaginary part actually. We are going to do a really dirty approximation now, okay? Just to find out something about the real and imaginary part. Like I said, it's going to be a really dirty approximation right here, and I'm terribly sorry if this triggers anyone. I'm terribly sorry, Hagoromochak, for using you on such a filth exercise. Okay, that's a really filthy exercise right here. Now, if we take a look at the gamma function in its Euler form, we had it before. We are going to do a really, really rough approximation. We are going to approximate this thing right here as just the first member of our product that we had. So 1 over 1 plus I, this is what we had right here, times the first member is 1 plus 1 to this thing right here, 1 plus I, over, and then we are going to get 1 plus z over k, z over 1 in this case, 1 plus I, leaving us with, okay, this is nothing but 2 to the first power times 2 to the I power, okay, leaving us with 2 over 1 plus I, 2 to the I power over 2 plus I. Now, we can actually multiply those two together, okay, to give us, now we are going to have 2 to the I power over, this is going to give us 3 minus 1, 2 minus 1, okay, I times I is -1, 2 minus 1 is just 1, and we are going to get 2i plus 1i is 3i. Now, this in itself already looks quite dirty, but the thing is we want to solve for real and imaginary part on this thing. Why not multiply this by the complex conjugate of this thing right here to get a real number down here? So 1 minus 3i over 1 minus 3i, that's a common practice you should do when solving for the quotient of a complex number. Meaning, down here we are going to get the modulus squared. Okay, it's the modulus squared, so 1 squared plus 3 squared is nothing but 10 in this case. So 2 over 10 down here, 2 to the I power, and then 1 minus 3i. Now 2 and 10 is going to cancel out to 1/5, okay? And also we have 2 to the I power. By the same argument we had before, this is nothing but e to the I times natural log of 2, okay? But this we can bring in the Euler form, so we have 1 minus 3i over 5 times the cosine of natural log of 2 plus I times the sine of natural log of 2. I'm kind of rushing through this right here. It's already taking us quite a long time to derive all of this. Now we can multiply it out. Okay, solving for the real and imaginary part. Let us see what we actually get. We are going to have a common factor of 1/5 right here. We are going to get the cosine, so that's the real part, cosine of natural log of 2. Then this is going to give us negative, and negative is going to become positive, plus 3 times the sine of natural log of 2. This has been the real part. And then plus I times 1/5 of, we are going to get, this is going to give us negative sign, so let's use this at first. So sine of natural log of 2. And then minus 3 times the cosine of natural log of 2. Negative 3 times the cosine of natural log of 2. Does this look like anything we can actually approximate? I'm so sorry. I didn't want to use you for something filthy like this, but you see, natural log of 2 is actually really small, 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 meaning we are going to use small angle approximation. I am so sorry, but I couldn't get any closer to this. I said it in the beginning, for here it does work wonders, but for this thing right here, this converges so slowly, no human being could approximate it by hand properly, okay? So let's just go through this. So this right here is approximately 1/5. Okay, small angles on the cosine is going to be 1, plus 3 times the natural log of 2. Oh, Hagoromo-chalk, I'm so sorry, my dear friend. Plus I times 1/5 of the natural log of 2 minus 3. It's getting worse. What is the natural log of 2? Well, it's natural log of 1 plus 1. And the cool thing, it's nothing but the alternating harmonic series, okay? Dirichlet eta function of 2. Take a look at that. It's quite easy to derive. Maybe I've already brought out the video regarding this topic. Now, it's the alternating harmonic series. Let's approximate it to for like, I don't know, 3 decimal places, for example, 4 decimal places, or members of the series. So natural log of 2 is approximately, we're going to get 1 minus 1/2 plus 1/3. Okay, let's do one more because the arrow is going to grow right here. Okay, minus 1/4. We know that this right here is nothing but 1/2, and this is going to be plus 1/12. Meaning, if we bring this together, we are going to get 7/12. 7/12. That's quite a nice approximation right here. So this thing is nothing but, okay, this is going to give us 7/12 minus 3 if we expand this fraction, so that's 36/12, leaving us with negative 29/12. And the cool thing is, this part right here is actually negative, okay? So it's supposed to be negative, this imaginary part, so that's already a good thing. At least we are going to get this out of this whole ordeal. Okay, we are going to get 1 plus 3 times this thing is 7/4, leaving us with 11/4, right? So this in itself is nothing but roughly, okay, once again it's an approximation, we are going to have 11/20 plus, okay, using the 1/5 right here, plus, okay, I times, it's going to be a negative number, 29/16. 60, not 16. Now, you can even approximate this expression right here using just this thing right here, and it's going to spit out a real part of roughly 1/2, and this is really good. So the real part is roughly 1/2. It's a really extremely small error you're going to get. Like I said, the real part is going to converge extremely fast, and here we roughly have a bit more than 1/2. Okay, so this real part in itself is pretty quite nice, but here comes the imaginary part. This thing right here, so the 29/16 is a little bit less than 1/2. It's negative, and that's good. So it's negative 1/2 roughly. But if you take a look at Wolfram alpha, and that's why I said the imaginary part is going to converge extremely slowly, like extremely slowly. This thing is not even close to the real value. I think the real value is something like 0.14 something, so this right here quite sucks, but it's going into the right direction. It's going to approach our value that we wish for really slowly. And that's basically it. I'm terribly sorry for using this fabulous jargon an approximation exercise. If you did enjoy this video, please like and subscribe, recommend channel if you like. If you want to support channel a bit more by the features I created, and up until next video, have a flammable day. See ya.